Through.
Yeah, she's getting, you're supposed to do her vitals. Oh, yeah. I love I'm having the hardest time. You were early.
Good morning. Is this mic on? Oh, it's dead. So.
Do you want me to go get batteries? I have a battery. Could you tell us if you were so straight?
Hello.
I just wanted to let you know there's some people setting up for clinics still
I
upstairs.
know when they need to get in the habit of being here on time.
Okay.
I know everybody's supposed to set up.
Okay. I just wanted to let you know.
It just, what direction?
Part two.
Awesome. Excellent. Thank you. All right. Now can you hear me? No? Yes? All right. Am I coming through yet? Can you hear me now? No? Yes? No? All right, folks, it is past time for us to get started. The microphone is not syncing this morning, so I will need you to keep down the background noise, and I will speak loudly, which I used this room for many years without a microphone, so we should be good. I would like to remind you that this is a no cell phone class, and your cell phone does need to be in airplane mode and in your backpack on the floor. And so, let me turn down the lights just a little bit more up front, and we'll get started. We'll get started with a word of prayer. Father in heaven, we thank you for another beautiful day, and we are so grateful that we're finally into spring and it's not raining quite so much, which is nice. I pray that you will be with us, both as students and faculty, throughout this day. We have many things to accomplish, and we appreciate your guidance and your support and your wisdom and your grace to sustain us through all of our activities. I pray these things in Jesus' name. Amen. We left off in our discussion of disease at a cellular level with one of our basic responses. So we just kind of barely got through them. But you will remember we talked about the cell having a specific function and a range of function that is its normal homeostasis. But when it encounters excessive physiologic stresses or truly pathologic stimuli, it can become injured generically. And we talked about 3 different patterns of cell injury that, and some of them have the word injury in them. So the combination of words is what makes it a specific pattern. But those 3 responses that are the typical responses are going to be either an adaptation, a reversible cell injury, or an irreversible cell injury that leads to cell death. We had time to talk about some of the specific patterns of adaptations, And we were really just starting our discussion of reversible injury. So we are still in this category right here, reversible injury. And remember that a reversible injury, by definition, is potentially reversible. That doesn't mean it will always be reversed, but it's potentially reversible, and the injured cell could return to a state of normal, or it could go to a state of adaptation. So those are kind of its options. But if the situation that's leading to the injury is not corrected, or if the cell encounters new or additional or different physiologic stresses or pathologic stimuli, that cell could end up passing the point of no return and dying. So we kind of pick up with our morphologic patterns of reversible injury. These are morphologic patterns that we see microscopically, that when we see them, we know that at least at this point, the injury is still reversible. That if the pathologic stimulus is removed and the cell is placed in a good situation, the cell could recover or at least move into a state of adaptation. We had time to talk about cellular swelling, which is the predominant morphologic pattern of reversible cell injury, where there's damage to the sodium pump in some way or another, so the cell takes on water in the cytoplasm and enlarges it. It literally swells up because of water on the inside of the cell. And so we move on to fatty change. Fatty change is quite a bit less common than cellular swelling, and it is really only an option in those cells that are normally involved in fat metabolism. It is more common in certain, even within that category, certain cells and tissues, and actually as a response to certain types of pathologic stimuli. But in fatty change, the reversibly injured cell accumulates simple lipid within the cytoplasm. What color are simple lipids usually? They're yellow. Fat is yellow. So what cells in the body are involved in fat metabolism? Do we know? Liver. Liver processes lots of nutrients, helps us store things that we don't use immediately, processes lipids into the appropriate size for the different cells to use for whatever they use lipids, because there are lots of different kinds of lipids. And actually, the liver is the single most common place that we see fatty change. Skeletal muscle and cardiac muscle and certain cells in the kidney can also use lipids in a way that if they become injured, we can see fatty change. But definitely this is a response that we see predominantly within the liver. And the liver can also have cellular swelling. So just because we can have fatty change in the liver doesn't mean that any type of reversible injury in the liver will be fatty change, because lots of the time it's going to be cellular swelling. So it kind of depends on the nature of the injury as well. What organ are we in this set of photos? Do you recognize? Kidney. So we're looking at glomerulus in the middle. On the left, we have as normal as I have in my files. So this is the glomerulus, and these are the tubules. This is the normal relationship. This is not a perfectly healthy glomerulus, but it's as good as it gets with my particular set of slides. So, because I am a pathologist and everything I have is pathologic, seems like. But anyway, this is our diseased set. Come on, go away. It won't go away. So, no, why is it stuck? Where do you see the major changes? Do you see the major changes in the glomerulus or the tubules compared to the normal? The tubules, exactly. So the renal tubules are very, very sensitive to both toxins and oxygen levels, and they become injured pretty easily. And you'll notice that the cells are larger and kind of grungy looking. Do you notice that they kind of look grungy? Like it's a dirty slide, only it's not. And you'll also notice that they're swollen enough that you don't see a nice lumen. so it encroaches on the lumen. So which pattern fits with that grungy, foggy look? Are cellular swelling. So this is a good example of cellular swelling in the renal tubules. And this is cellular swelling in what organ? Recognize this one? This is liver. So we have cords of liver cells. They should look like this, but we are seeing swollen cells with that kind of foggy, grungy cytoplasm. So that fits with our cellular swelling. This is fatty change. The two livers on the left both have fatty change. The one on the bottom has mild fatty change. The liver is enlarged somewhat, and it has a little bit of a marbled appearance. Normally the liver is kind of a rich red-brown color, and this one has a little bit of yellow and brown marbled. The one on top is very enlarged because of the accumulation of lipid, and it is also very, very yellow. When we do autopsy examinations, we remove the liver, we weigh it, so we know if it's enlarged. Usually you can tell by looking, but we always have to have objective measurements. And we also slice through it. So when you took anatomy, did you slice through the organs? No, you just really identify them. But when we're doing postmortem examination, we slice through and we look at the different slices, trying to find any pathologic lesions within the tissue. And when you slice a fatty liver, your knife comes out greasy. It is fat within those cells, lots and lots of fat. So this is fatty change. Guess what is the single most common cause of fatty change in the liver? What type of assault? No guesses? Alcohol abuse. Alcohol abuse. But this is the reversible pattern of liver disease associated with alcohol abuse, because fatty change is a reversible injury. So if the person stops drinking excessively, both of those livers could have gone back to normal. These were taken from autopsy examinations. The patient didn't die because of fatty change of the liver. It is a reversible injury. It's not a lethal disease, but they happen to also have it. When we look histologically, we see that the cells are enlarged and they have these droplets within them. And we know the droplets are fat and not water because we can do special stains. Come on, go away. And we do an oil red O, and that all lights up bright red. And that helps us know that that's not water and that it's lipid. So that's fatty change. Those are the only two predictable morphologic changes that tell us that a cell injury is reversible. Do you think we always take tissue samples when a patient has a disease that we think is reversible? No, we don't. So we don't always have the opportunity to look at the morphology, because many injuries are quickly reversible, clinically diagnosed and managed, and don't require sampling of the tissue for diagnostic purposes. So we move on to cell death, that last and final pattern of our basic responses to a pathologic stimulus, where we have a one-way arrow and there is no return. Question? When people have liver transplants, it's not because of fatty change or anything? No, liver transplant would not be because of fatty change. They would have to have much more serious liver disease. Much, much more serious. Usually cirrhosis, which is advanced and irreversible. Many causes of cirrhosis. So let's talk about cell death. There's actually several different ways that cells can die, and there's one predominant way and some lesser common ways and some newer ways that we're just beginning to recognize and understand. We're going to talk about the two that we best understand and are most important for you to know about. The typical way that cells die is what we call necrosis, and that is when we go through the pathway of a reversible injury first, where the injury progresses in severity, passes the point of no return, where the cell cannot recover and so it dies. And We know that we can't always identify that exact moment where the cell has passed the point of no return. A lot of thought and investigation has gone into trying to figure out really what is it that constitutes this point of no return? When is it that the cell cannot recover? And we've identified two major things. When we have such profound damage to mitochondria that we cannot restore energy production and we cannot have enough energy production for the cell to have even basic minimal metabolic needs met, the cell is going to die. So it has to have energy. So that's an important thing that contributes to that point of no return. And the other thing that's very important is when we have really severe damage to cell membranes, predominantly the plasma membrane on the outside of the cell, but we can also have such profound damage to organelle membranes that the cell will die. And that's actually one of the ways that we can lose mitochondrial function, is for the mitochondrial membranes to be so damaged that the mitochondria can't work. So if the outside plasma membrane on the cell literally falls apart and can't hold the cell together again, it makes sense the cell is going to die. But sometimes it doesn't fall apart, it just becomes completely dysfunctional. Sometimes we think about plasma membrane as a wall, but it's not just a barrier that keeps things in and other things out. It's a very functional part of the cell. So if it becomes damaged in a way so that it has no functionality, that will kill the cell as well. So those are things that constitute the point of no return. Most of the time when cells die, it is through this pathway of a reversible injury first that escalates, passes the point of no return, and the cell dies. So necrosis is a word that you should think of as being the common ordinary way or morphologic pattern of cell death. The other pattern of cell death that's like second most common, but still a very distant second, way down low, is apoptosis. It's a Greek word. The Greeks say apoptosis. The rest of the world says the P is silent and call it apoptosis. I don't care which term, the way you pronounce it. But it's a vastly different pattern of cell death that is intentional, and we'll talk about it separately. We're going to talk about necrosis in more detail first, since it is our predominant way that cells die. So the cell starts out living. It is attacked by some type of pathologic stimulus, one of those things like hypoxia, trauma, chemical toxin, all those different kinds of things that constitute assaults on cells. So it's assaulted, it sustains a reversible injury that progresses, passes the point of no return, and the cell dies. When this happens, we see the morphologic features that we recognize as necrosis because of two different kinds of events that occur. Usually it's one or the other, not both at the same time. They're kind of, it doesn't work that way. You have one or the other. We see necrosis morphologically because the dying cell is being digested by enzymes. It literally kind of breaks down to liquidy mush when it's digested by enzymes. Those enzymes can come from different sources, and so we have different terms for the enzymatic breakdown of the dying cell depending on the source. We use the term autolysis, lysis for digestion, auto for self. So automobile is a way we can move ourselves in some type of vehicle, but it doesn't mean car, it means self. So autolysis means self-enzymes are breaking down the cell. The cell's own enzymes. Where do the cell's enzymes live? You know, I hear a lot of clicking on keyboards. Are you guys trying to write down everything I say? You should not be doing that. You should be using your handouts and just supplementing it. If you're trying to transcribe everything I say, you are not learning. You are being secretaries. You are not secretaries. So if you need help with your note-taking skill, you should make an appointment to meet with me, and we'll work on that. But you should not be transcribing everything I say. You should be thinking about what I say and adding to your notes what's not there, okay? That will help you a lot. Otherwise, the amount of information you accumulate is so massive, you will be overwhelmed by it and you will not succeed. It will interfere with your success. So we move on. I'm hearing massive typing that worries me. Okay, we move on. Heterolysis is the other source of enzymes that can break down a cell, digest it in the process of cell death. Hetero means other. So that means that the lysis, the breakdown and digestion of the cell, comes from enzymes from outside the cell. Inside the cell, the source of enzymes is from the cell's own lysosomes. So it means that we have damage to the lysosome membrane in a way that those enzymes are being released within the cell and digesting it from the inside out. In heterolysis, we have enzymes that are coming from neighboring cells, maybe inflammatory cells, other dead cells, but not the individual cell that's dying. So enzymes from outside the cell are acting on it, and sometimes those enzymes actually come from outside the host. They could be enzymes from bacteria or something like that. But in the situation of heterolysis, the dying cell is being digested from the outside, and then everything breaks down. So that's autolysis and heterolysis. The other basic process that can happen is denaturation of proteins. Question?
You had asked a question like where do enzymes come, but you didn't answer it.
Yes, it did. After the fact, lysosomes.
Oh, I didn't hear it.
Yeah. So the lysosomes break down. And lysosomes contain very potent enzymes. Normally, the way we release lysosomes on things that need to be digested is for the lysosome to fuse with a membrane-bound sac that has whatever it is that needs to be broken down. So the lysosomes are always contained within a membrane. But in autolysis, they are free-roaming within the cell and everything gets digested because there's no control over them if they're not contained. Denaturation of proteins is like cooking an egg. It solidifies and it becomes non-functional. So certain types of injuries will cause denaturation of all the cell proteins, so the cell becomes completely non-functional. But it's also solidified and frozen, kind of, so it doesn't go to liquidy mush, it actually gets firm. And when we have denaturation of proteins, the dead tissue is firmer than normal instead of softer than normal. So it's kind of interesting how those two processes have opposite effects grossly on the tissue. When we were looking at changes that characterize reversible cell injury, we were looking at the cytoplasm of the cell, correct? Accumulation of water in the cytoplasm or accumulation of simple lipid. When we are trying to identify if necrosis is present, we can't just look at the cytoplasm because necrosis goes through the pathway of reversible injury first, so we already know there are going to be changes in the cytoplasm. So we have to look somewhere else. And it turns out that the key features that tell us the cell is dying or dead are in the nucleus of the cell. The nucleus is fairly normal in reversible injury, but the nucleus will show profound changes when there is necrosis and cell death. And there are several different patterns. And those different patterns are dictated by those two different processes of either enzymatic breakdown of the dying cell or denaturation of proteins. One of those nuclear changes is called karyolysis. Karyo refers to the nuclear body. What does lysis mean? Breakdown. So what kind of process is going on in the dying cell to produce karyolysis? our enzymatic breakdown. Our enzymatic breakdown of the cell. Whether it's autolysis or heterolysis doesn't really matter, but when we have enzymatic breakdown of the cell in general, it's going to produce enzymatic breakdown of the nucleus also. And what we will see if we sample the tissue and look at it under the microscope, we will see that the nucleus fades and then disappears. What does the nucleus normally look like? What color is it? You've taken histology. Which stain does it pick up? Picks up the blue stain. Do you remember the name of the blue stain?
Methylene blue.
That's not the routine one. Routine staining is H&E. You remember what those stand for? Hematoxylin and eosin? You learned the H&E so long ago you've forgotten. Hematoxylin is the one that's the blue stain, and eosin is the red stain. So normally the nucleus is a pretty intense, distinct blue. So in karyolysis, it becomes lighter and lighter blue until it disappears. And so that's what we recognize as karyolysis. Another major pattern of cell death at the nuclear level is pyknosis. And in pyknosis, the nucleus shrinks and becomes darker blue than normal. And this is because of denaturation of all the nuclear proteins. So it's like the nucleus got cooked. That's a good way of thinking of it. The nucleus got cooked. It's completely non-functional, but you can see it. It persists either until the host lives and removes that dead cell, or some enzyme source comes to digest it away, or the host dies. Those are kind of the outcomes. But it's kind of freeze-dried, and so is the whole rest of the cell. There is a lesser common pattern of nuclear change that we sometimes see that's called Karyorhexis. It is a later event that sometimes happens in the situation of pyknosis. The pyknotic cell can persist long enough to have some enzymes come in that break the nucleus into some big chunks. They're not dissolved yet, but we have some big chunks. So we see nuclear fragments. And they're still darker blue than normal because they're freeze-dried, but they are broken into chunks. So we only sometimes see that. So definitely the major patterns of nuclear changes that you need to remember and understand are karyolysis and pyknosis. Those are the major ones. Just like we see nuclear patterns that we identify with cell death, where a reversible injury passed the point of no return and became irreversible, we also have patterns of necrosis that we see at a tissue level, where we have collections of cells, maybe a big collection of cells that are dying, and we can see specific morphologic changes that we recognize as necrosis. There are two major patterns of necrosis and a few minor patterns that we see in special situations. Our two major patterns of necrosis at a tissue level are coagulative necrosis and liquefactive necrosis. And it should be no surprise that which one you get depends on if you predominantly have denaturation of proteins in the dying cell or you have enzymatic digestion. So we're seeing a theme. And you should be able to figure out what nuclear change you're going to be seeing in these patterns as well. Coagulative necrosis is the one where we get denaturation of proteins dominating. So what are we going to see in the nucleus? Pyknosis, absolutely. A dark, small nucleus, and all the cytoplasmic proteins are also going to be denatured. So we see preservation of the basic shape and outline of the cell, some altered staining properties because it is freeze-dried, so to speak. It's a cooked cell. But it persists, and you can see it, and you can tell usually what type of cell it's supposed to be. And there are lots of different kinds of things that produce coagulative necrosis. It is the typical pathway of irreversible injury when the underlying cause is hypoxia, which is a very, very common cause of cell death. So if the cell doesn't get enough oxygen, can't utilize oxygen for energy production, that causes denaturation of proteins and our cooked cell with the pycnotic nucleus. A very common situation where we have irreversible hypoxic injury is myocardial infarction, our common heart attack. So we would see preservation of the myocardial cells with a pycnotic nucleus. And it's going to be firm. What color do you think it's going to turn? What color is the heart normally? It's a deep red-brown, but it's quite red. If a person dies of myocardial infarction and they have a postmortem examination, if they live enough hours, because it usually takes about 8 hours for the morphologic patterns of coagulative necrosis to show up. If they live that long before they die, and you look at that heart, the dead area is going to be firm and white. It actually turns white, just like you cook an egg, and the egg white turns from clear to white. In coagulative necrosis, the cells turn white. Kind of interesting how that happens. Liquefactive necrosis is the other major pattern of necrosis at a tissue level. And in this one, the major process that's involved in the irreversible injury is the enzymatic breakdown of the cell. So what are we going to see in the nucleus? Karyolysis, absolutely. If the patient lives long enough for you to take a look at this, and again, it takes about 8 hours for the morphologic changes to develop, you're going to see fading away a light blue nucleus and some of the cell cytoplasm breaking down and maybe the cell outline becoming blurred. Can't always tell where one cell starts and another one ends because it's being digested away. Common events that lead to liquefactive necrosis are severe bacterial infections. Usually this is because of enzymes from the bacteria themselves that are digesting and killing host cells. But sometimes it's also because of the host response, trying to kill the bacteria, also killing some host cells, because those inflammatory cells can release enzymes into the tissue as well. So focal bacterial infections are a good example of liquefactive necrosis. What does focal mean?
Just one area?
Just one area, usually a small area. Localized and focal usually kind of mean the same thing. Small, kind of not all over the place. We also see liquefactive necrosis in irreversible hypoxic injury in the brain. Everywhere else in the body, irreversible hypoxic injury produces coagulative necrosis, but the brain is different, and maybe that's because it's soft and has so much lipids. I don't know, it's just a different kind of tissue. But if your brain undergoes irreversible hypoxic injury, you have a stroke that cuts off the blood supply to the brain, it will undergo liquefactive necrosis. And the dead area actually cavitates, becomes a hole filled with liquid, just truly liquid mush. And there are a few other things that can do that. So let's move on to some special patterns of necrosis that we sometimes see, and we apply these terms only in those specific contexts. One of them is gangrene. The more proper term is gangrenous necrosis, but who says that? Everybody just says gangrene. This is different than gas gangrene. Have you ever heard of gas gangrene? Gas gangrene is actually the result of a very specific infection. And why they have to use another word that typically means something else is beyond me. But gangrene is a pattern of necrosis that occurs when we have compromised blood supply, specifically ischemia, that produces irreversible hypoxic injury to the tissues in a special location. Don't you think we can have localized loss of blood supply producing irreversible hypoxic injury anywhere in the body? Sure. But we only use the term gangrene when it's in the extremities. What are the extremities? Hands, the parts of your body that are farthest away from the middle part. So feet, toes, hands, fingers, those are the extremities. When we get gangrene, because it is irreversible hypoxic injury from ischemia, from loss of blood supply, we are going to get, here I want to back up. We are going to get coagulative necrosis, but it can do some special things after that. And we've got some pictures, we'll talk about the special things. So gangrene is initially characterized by coagulative necrosis, but then it develops some special features that make it different from our traditional coagulative necrosis, and that's why we call it gangrene. And part of that is because it is in the extremities. Caseous necrosis is another special pattern. It is dry, white, and cheesy necrosis that occurs only and exclusively in tuberculosis. So it is a morphologic pattern of necrosis that is pathognomonic for tuberculosis. And fat necrosis is a special pattern of necrosis of fat tissue around the pancreas. And we'll talk more about that, but we're going to look at pictures first. So gangrene or gangrenous necrosis occurs in extremity because of loss of blood supply. Often occurs in diabetics. It can be seen in other situations as well, but it often, very often, is in diabetics who also have peripheral neuropathy, and they can't feel their extremities because of nerve damage. When you can't feel your feet and toes, you ignore them. It's like they don't exist. So you don't seek medical attention when something is going on. So what often happens in gangrene is that a toe will die because of loss of blood supply. It undergoes coagulative necrosis, but nobody does anything about it. And so it dries out and becomes black and leathery, and it can stay that way for a long, long time. Months. And it can also progress and get a bigger and bigger area. When it's dried out and leathery and brown to black, we call it dry gangrene. That's when it's still in that stage of coagulative necrosis. But when you can't feel that toe or that foot that has gangrene and you don't take care of it, it can also get secondary bacterial infection. And if bacteria move into it, they bring enzymes that then transition to liquefactive necrosis. And so it starts getting soft and greenish and mushy, and then we call it wet gangrene. It doesn't start out wet gangrene. It always starts out with coagulative necrosis. So we only get that transition to liquefactive necrosis when we have secondary bacterial infection. Then it starts to stink, and then they know that they have a problem, even though they can't feel that foot. It's got the dead toe, but it does stink. How do they treat gangrene? Cut it off, amputation. So when I was a resident, we got amputation specimens on a regular basis. Normally in surgical pathology, we got specimens in jars of formalin. Biopsies would be little teeny jars, surgical specimens, big jars. Toes will fit in a jar, but we'd get whole feet or lower legs because it progressed. So they would put them like in a black bag, trash bag, and just dump a little formalin in for fixative. Not enough. You're supposed to have 10 times as much formalin as the size of the specimen. They never had that much. And then it would get stuck in the refrigerator on surgical paths. So when we had an amputation specimen, we'd have to go to the refrigerator, open the black bag that wasn't adequately fixed, and the smell, if it's liquefactive necrosis, wet gangrene, the smell is outrageous. It's awful. Yes.
Have you ever passed out or got so grossed out that you had to leave?
Nope,
Or you just-
no, not me. I did pretty good. I was also the one who in dental school had anatomy lab right before lunch and actually ate my lunch with sandwich in one hand, my hand in the body on the other side, because I got sicker from having no food in my stomach. They won't let you do that anymore, have food in the anatomy lab. But I did. 11:30 would hit, I'd start getting sick, the sandwich would come out. Sandwich in one hand, hand in the body in the other. So I have a pretty tough stomach, but I don't recommend that. You don't recommend that. The one time I had a problem was actually with a patient. We had to go pick up a specimen in the OR with an adolescent male who was having an aspiration bone marrow biopsy for leukemia workup, and he was awake, and it was very painful. And watching him be in pain, I got very lightheaded. I was having trouble with that. Yeah. So I don't like to watch suffering. Nope, not me. We move on. Yeah, so sometimes in dry gangrene, the dead part can fall off. And then the one on the right is the wet gangrene, and you can see it's breaking down, turning greenish, getting mushy, and kind of nasty. Yes. Yes.
You said it's from diabetes. Is there anything else that might cause
Anything that can cause loss of blood supply in an extremity can produce gangrene, but usually when tissue dies, it's associated with a lot of pain, and people get prompt attention and get it taken care of before it progresses to the point that it's leathery and black and dried out. And so it doesn't usually progress to the point of full gangrene except in diabetics or other individuals who have no sensation, like people with a spinal cord injury or something like that that have no sensation. So that's why we see it more in diabetics.
it never goes to wet unless it starts out?
It starts out with coagulative necrosis. In some situations, it can go to wet gangrene fairly quickly. In other situations, that it can be dry and nasty for a long time before it gets secondary bacterial infection.
So people are more educated now about this in diabetes. Do you see less of this now? Because it can be obvious to see your turn black and...
But people don't look when they don't feel. That's the weird thing. So if a person has another person that helps care for them, that can see things and make sure they get good care, then we don't see much gangrene. But there are a lot of people who don't have anybody taking care of them. They're kind of on their own. So we surprisingly see gangrene still. Maybe not quite as commonly as in the past, but yes, it still happens. A lot, sadly. Yes?
So I could deduct that all necrosis is from hypoxia?
No. All of those things that can constitute assault on cells could produce an injury that passes the point of no return.
Okay.
But gangrene is always from hypoxia. It's always from loss of blood supply. Caseous necrosis. Casein is milk protein. And caseous means cheesy. Literally, it means cheesy. Pathologists like to name things after foods. I'm not sure why that is. Maybe because we're always hungry. But caseous necrosis is a special pattern of necrosis that we see in diseased tissue in tuberculosis. And the tissue becomes very firm and white and kind of dry and crumbly, like feta cheese that you crumble on your salad. I love feta cheese. It may take you a few days to think about it the same way after looking at this picture, but it's similar in consistency to that. So somebody brilliant named this caseous necrosis. It's cheesy. And tuberculosis most often affects the lungs. It can affect other areas. And you can see multiple areas of caseous necrosis. And if you look closely around them, they kind of have a gray solid zone around them. That's the living tissue. that has the tuberculosis infection. And then there are some more normal areas of lung in between the areas of active disease. So there are multiple areas of caseous necrosis in this particular example. But it is truly dry, white, and cheesy, and it is a pathognomonic sign of tuberculosis. Nothing else has caseous necrosis. Fat necrosis is a term that we use when we get necrosis of the fat around the pancreas. There's quite a bit of fat around the pancreas, and I suppose there could be multiple events that produce necrosis there. We use the term fat necrosis specifically when we have activation of pancreatic enzymes in the pancreas and surrounding fat itself. What is the job of the pancreas? What is the job of the exocrine pancreas? There's endocrine pancreas, makes insulin and other things. There's exocrine pancreas, which makes enzymes to digest our food. And it dumps those enzymes into the duodenum, where it interacts with our food and digests it. So the normal role of the pancreas is to make very powerful digestive enzymes, but those enzymes are not active in the pancreas. They actually don't transition to their activated form until they get into the small bowel. But in some situations, we can get premature activation of those pancreatic enzymes while they're still in the pancreas. And because they're powerful enzymes, they start digesting away the pancreas and the fat in and around the pancreas. When we get digestion of the fat in the pancreas, it combines with calcium and actually produces a soapy-like substance that's kind of pale and creamy and firm, and that's the fat necrosis. How do you think a patient is going to feel if their pancreas is being digested away? Do you think they're going to have symptoms? Yes, it is associated with severe abdominal pain. And so these are patients that usually end up in the emergency room and they don't know what's going on for sure. They go into emergency surgery for laparoscopy. The surgeon finds these little deposits of firm, creamy stuff, and it looks like metastatic cancer. So they take a sample of it, they send to the pathology department for rapid frozen section, and it ends up just being fat necrosis. So the patient has been saved from the cancer diagnosis, but they still have a very serious situation going on with the pancreas, and they have to work very, very hard to stabilize the patient and save them. But they often can be saved. Yes.
So these are the pancreatic enzymes that are eating away at itself if they're not moving properly?
Mm-hmm. But the fatty acids that are produced and released combine with calcium to make these firm areas of dead tissue. But the concern about it is sometimes the misdiagnosis of cancer. So we have looked at our basic responses of adaptation, reversible injury, and irreversible injury. And we have a few little miscellaneous things that we want to talk about. So all of those should be familiar. Yep, see, we talked about those. So where do we want to go next? Oh, I want to look at this first. Forgot I brought this. The normal cell that sustains a reversible injury, we saw changes in the cytoplasm. Cellular swelling, when it takes on water, it could take on fat or lipid, but this particular diagram is cellular swelling. Lipid within organelles, lipid within the cytoplasm, even little bubbles of lipid under the surface that we call membrane blebs. We didn't talk about those, but that's what it looks like. If it recovers, it'll go back to normal. Slow pathway back to normal. If it passes the point of no return, it will undergo necrosis, fall apart, solidify, one or the other. Either undergo coagulative necrosis or liquefactive necrosis. And this one is kind of a combination of the two, so we can't talk about that. But we see nuclear changes and cytoplasmic changes when we have necrosis. This is a set of pictures that show changes that we've talked about in real tissue. So this is a heart that has been sectioned this way, and it has a very, very thick wall on the left side because of hypertrophy. So that heart was having to work a lot harder to maintain cardiac output, so the cardiac muscle cells underwent hypertrophy. We saw hypertrophy microscopically. This is what it looks like grossly. Just a really thick wall, heavy heart. This one is supposed to be as normal as it's going to get, although we have some little pale areas. We might have some reversible injury there. What do we see here? It's the white one. It's kind of creamy white. If you were to palpate that, that would be firmer than normal. This is our coagulative necrosis. This is a person who had myocardial infarction, our traditional heart attack. And actually here we have a place where a ruptured blood vessel, because even the wall of the blood vessel is dead, it hemorrhaged into it, and the patient didn't survive. What are these white areas? This is white. That's white. Those are scars from previous myocardial infarcts that were much, much smaller and the patient survived. But they didn't survive the last one. So we see some coagulative necrosis. We want to talk about apoptosis next, but our time is done, and I know you guys have to rush to the clinic. We're a little behind schedule with lecture. We have plenty of time in the next couple sessions to get caught up, so we're not too worried about it. I had wanted to have a quiz on Friday over our first topic, but we haven't finished it yet. So no quiz on Friday, we just need to get caught up, okay? And I will see you Friday morning at 9 o'clock.
Would that be Caseous?
No, because it's not tuberculosis. We only get Caseous with tuberculosis. It would just be coagulative. So Caseous necrosis is whiter and it's more localized. It has a really sharp edge to it too. Oh, sorry. This is more spread out, and it's not the brilliant dry crumbly white that we see with Caseous. So even grossly, they look different, and histologically, they look different as well.
Yeah, I forgot about the stripe.
Yeah, that's a key thing.
I said it was white. All right,
No,
thank you.
that's right. I have to meet with Dr. Grandi. We have to go over the schedule and the syllabus, and we both have a very busy week. And I was scheduled almost every minute of the day on Monday, and yesterday was my private practice day, so we haven't been able to get together yet. We're hoping to today. I had hoped to have everything finished by the end of the week and posted before the end of the week, but it could be over the weekend that I have to finish it.
Okay, so in terms of exams,
I have tentative dates for everything, but I don't have, the final exam isn't even on the 5th floor schedule. We just